Okay. So good day, everyone. I want to just take a moment to introduce our speaker today.
Can people actually hear us? Have we confirmed this? Yes, I see a thumbs up.
Okay, thumbs up. Okay, good. All right. So we'll try to figure out, let other people talk in a little bit, but let me begin and turn it over to Ken. So we're happy to have Ken Wharton come visit us today. Ken is his bachelor's of science was at Stanford University, and then did his PhD at UC Los Angeles, and he's currently a faculty member at San Jose State, but has now recently moved to the greater Los Angeles area. So we hope, being an incorrigible Californian, as it were, he will come visit us frequently here at Chapman.
Only a 1 hour drive, yeah.
Exactly. So Ken's interests are in the foundations of quantum mechanics, and he's become especially famous about thinking about retrocausal models of ways of understanding quantum mechanics. And so we're very pleased that you've taken the time to come visit us. And so I'll turn the seminar over to you.
Wow, I think infamous would be more famous. Okay, good. Thank you so much, Andrew, for having me here. And let's get into it, because I think I was writing this. This is a brand new talk. I'm trying out a bunch of stuff on you guys all at once, setting up some new results, talking about some new results, and I don't really know how it's going to go. So thanks for being my guinea pigs on this. And lots of feedback, of course, is welcome here. Okay, so let's just start with all the great things about doing things with Lagrangians rather than Hamiltonian. So rather than solving the universe one time step at a time like a computer, instead solve it all at once with some action principle. So Lagrangian is invariant scalar. All the quantum fields people invent are all based on, okay, what's going to be a nice invariant property here. And at the beginning, anyway, before you quantize anything, they're all associated, all these Lagrangian densities are associated with space-time regions. So it's like we get our space-time, we get our Lorentz covariance, and better yet, we get GR-friendly story, right? Because it's naturally coordinate independent. It doesn't matter how you slice the universe, it's just one big block. The choice of coordinates is nicely irrelevant. You don't have to think about particles. You can easily transition to fields. In fact, all of quantum field theory is, the standard model itself is a big Lagrangian density of fields, right? I mean, that's kind of the starting point, the standard model. And of course, hopefully you know that you can do pretty much all fundamental processes with actions and Lagrangian. So it's a really nice, beautiful starting point. A couple more points is that, well, don't know what the action is, but for now, let's just call it the time integral of the Lagrangian. But it's a global scalar. It's just a number, right? In principle, we're going to treat it as more than a number, or we can't get anything out of it. But it is a scalar, and it doesn't apply to a point in space-time or a moment in space-time. It applies to all of space-time, right? You integrate over all of space and time in principle to get the total action. So it's non-local in that sense, but it's built up from these Lagrangian densities, which are localized. And of course, hopefully you know that there's a deep connection to quantum theory, which is largely what I'm talking about for the first half today. And one really obvious thing is just the units are the units of h-bar. So that's my motivation for, we should think about the action in context of really everything fundamental, but definitely in terms of quantum foundation. And of course, people have, right? Because this isn't news. The very first big successes after the Bohr model of in quantum theory, where people started quantizing something. Well, it's called action quantization. It's not really the action. Actually, you see, I put scare quotes around the action. There are about 10 different actions in the literature, and there should be more, but people mean different things when they say the action. But anyway, we'll talk briefly about Wilson-Sommerfeld action quantization, where you take the abbreviated action and set it equal to NH. And then something a lot of people don't even know is that this was actually the original motivation for Schrodinger to quote unquote derive the Schrodinger equation. He started with a Hamilton-Jacobi action, yet another action. And then Dirac basically started poking about at how Lagrangians connected to quantum mechanics, wrote this paper that Feynman found in 41, and the rest is history with his thesis. People think of it as a 48 paper, but really he actually wrote it up in his thesis in 41, showing how the path integral essentially worked for quantum theory. And now he's yet actually another action that shows up in quantum mechanics. So there's a quick history of all the places that quote unquote the action has shown up. And yet, despite our love of the action, most people in quantum foundations don't pay much attention to the action. They just quickly use it, if anything, to get to the Hamiltonian viewpoint and then forget the action. It's gone. All this beautiful covariance and invariance I talked about is nowhere to be found in quantum mechanics. In fact, the time slicing becomes crucial, right? Even in quantum field theory, how you slice up the universe. Where's space-time? Everything was originally based on space-time. It's gone. We're off in configuration space and Hilbert space and Fock space, and we've lost space-time. The boundaries that we use in the action principles, we are used to boundary conditions as initial constraints and final constraints, but actually, as we'll talk about, the constraints you mathematically impose on the action don't actually match the constraints you do in the lab. And there is no way, actually, currently, to match up the constraints you put on a physical system in the lab to the constraints you use on an action principle, which is kind of weird. They're both boundaries, but they're applied very differently. Time-like versus space-like surfaces are treated totally differently in quantum mechanics, but they're treated the same way in action principles. Just a big boundary on the surface you're calculating the action. And just in general, even though maybe it's slightly rising in popularity, this all-at-once viewpoint where you're solving a whole system as a big block rather than as one time step at a time, it's not a popular viewpoint in foundation. Where the all-at-once approaches are definitely still quite marginal. And despite the fact that this is how action principles work and everyone loves action principles until it comes down to actually doing something. So that's my motivation for the outline here. Oh wait, one more point I want to make, and that is, how should I put this? People tweak everything in physics. You'll get an equation of motion, and people say, well, what if we add a new term? What if we add more dynamics? What if we mess around with the ontology? What if it's, not particles, it's fields, it's this, it's that? We come up with all sorts of crazy things. But compared to all the tweaks we do in all the foundational physics, the way we use the action is pretty cut and dry. It's like people do 2 or 3 things with it and refuse to consider anything else, or just don't consider anything. So that's just what you do with the action. And I will say that basically if you get one lesson out of this, is that we could and should be a lot more creative when it comes to action principles than just doing the same thing over and over again. Right? People introduce new terms to Lagrangian density, but they don't do anything different with S in the path integral. So why not? Let's be creative and curious. Okay, so that was my last motivation point. Let's see where I'm headed. So let's first talk about classical physics, right? We got to see where action comes in classical physics, and you'll see why I call this the 4D action versus the 3D action functional that we use for the Hamilton-Jacobi action. It's not that the action is living on 3D, it's that the boundaries are in 3D. And basically what we're going to see is action constraints, taking the action and putting some constraint on it is really successful way to whittle down all the possible universes into our universe. So that's kind of the message of the first half of this talk. Then I'll talk a bit more about more motivation that I've talked a lot about in the past, that this approach that has successful to these other parts of quantum physics could also be successful to entanglement, and there's lots of reasons to think that solving entanglement problems all at once is the right way to go rather than one time step at a time. And then to sort of illustrate this, I'm going to take one particular entanglement experiment you can do in the lab and give 3 different accounts of it. I'll give you the usual non-local magic distance, attribute distance story, the missing in action story, as I call it, the Feynman path integral, which of course has the action in it, but how do you interpret that? We'll talk about that. And then I'll do something new that you probably would be surprised about, that at least for certain entanglement experiments, maybe one at all, there is a one history account in terms of classical fields. So that's the new stuff that's just been submitted to Physical Review A, but it's not on the archive yet. So this is the first time publicly talking about this result. And I don't know if my co-author, Emily Adlam, has made it here, but I'll bring her up when the time comes. Okay, ready, set. Sorry. Okay. Let's talk about picking a space-time region and calculating the classical particle energy. So I just picked, now whether or not we can actually do this for any space-time region is an interesting question. Maybe we can talk about that afterward. But let's imagine we have a space-time region with 3 particles in it. And let's not restrict those particle trajectories in any way. We can have any path we want for these 3 particle trajectories. And of course, there's probably interactions between them. So the Lagrangian function down here is not only a function of the action of the 3 particles, but also a function of like the products, the interaction Lagrangians that all show up in here. So it's some complicated expression, whatever it is. This sort of magical thing happens when you build the action. You integrate over all this region, well, in time now, because it's just Lagrangian, not Lagrangian density yet. You integrate in time, and now you have S as a functional of all of these particle paths. So the inputs to the action here, you think it's a scalar, but what are the inputs to generate that scalar? It is basically 4-dimensional input, right? It's not just where they are in space, but their world lines, and there's no restriction on the middle. Now that's particles. Fields looks a bit different, but not really that different. You have some fields in space and time. Say this is the maybe it's the vector A field in electromagnetism or something. And you build a Lagrangian density now out of the field values everywhere in this block and the local derivatives of the field everywhere. And I guess if you wanted to, you could add more derivatives. And so now it looks a lot like it did before, except now you're integrating over space and time. If you want to make this a covariant integral, you put the square root of minus g in there. And you basically now have, again, this 4-dimensional input, right? Any field goes. You can do this for absolutely any field. It doesn't have to obey any equations. But here's where the magic comes in. The magic comes in, okay, now we have this action. Let's go back to particles for a second. Let's fix all the initial and final particle positions, but not the velocities, right? We let the velocities wiggle as much as we want. We fix the initial and final velocities, and we extremize the action. We say, I'm looking for the case where any little tweak to this trajectory doesn't change the action. And presto, you get out the dynamical physics equations we know and love, Euler-Lagrange equations, the Hamiltonian formulation. We get ordinary dynamics. You can do the same thing here for the field story. Now the corresponding boundary is that you fix all the field values, and of course the spatial derivatives along the boundary. This is a big hypersurface, right, in 4 dimensions, if you can picture that. But you don't fix the normal derivatives. You don't fix the field derivatives normal to your hypersurface. And then you do the same thing. You extremize the action, and boom, you get, well, in the case of E and M, you get Maxwell's equation, right? You get the usual dynamical equation. So we've seen this, many of you, but I want to point out a couple things you probably haven't thought about. One is that before, we haven't gotten to quantum or anything yet, but check it out. We have something that maps to the old school uncertainty principle. What I mean by the old school uncertainty principle is Heisenberg's original story where there were initial positions and velocities, you just didn't know what they were. And so check it out. What are you imposing on this path boundary here? You're imposing positions, and the velocities are not imposed, right? They're free. So that matches actually the uncertainty principle. If you measure in coordinates. Too bad, it only works with coordinates. And you might say, point I'll make later, wouldn't it be nice if there was a way to get out Euler-Lagrange equations where we made a momentum measurement, right? Or an energy measurement on the boundary. Why doesn't this procedure work then? And it doesn't work because of boundary terms, but maybe there's a way around it. So one kind of point I want to make here that it's kind of quantum friendly right from the beginning. But take a zoom out here and just think about what this magic process just did. We started with any possible universe, any possible particle trajectories, any possible fields, and then we put some conditions all at once. We said something about this non-local scalar has to be true. We impose that condition, and what do? We select ordered universes. We select the universes that obey our usual equations of motion, that obey all the usual relativistic causal relationships in the sense that you don't want faster than light causation going. That just pops out just by doing this. And I will point out, though, that we have not yet determined the universe, right? This doesn't solve the universe. What it does is it takes the action from something where you put in four-dimensional data, the whole bulk. But once you do this procedure, the bulk is pretty much determined by the boundaries. The boundaries live in 3 dimensions, right? It's this hypersurface around the 4 dimensions. So you still have an action functional. Even if you do this process, it's just now the action becomes a 3D functional. You put in the boundary data and determine everything else. So you've whittled down the number of random universes to nice ordered universes that look a lot closer to ours than we started with, just by putting this action constraint. Well, why stop there, right? We're not done with the action. We still have this 3D action functional. Can we do it again? Can we put some other constraint on the 3D action to further whittle down all the spaces of all the classically ordered universes to look like a quantum universe? And, well, there's a lot of evidence that we can do that. One random point I'm going to throw out here is looking at classical action extremization and just asking formally, is it retrocausal or not? Looking at these pictures, this doesn't look retrocausal because we have no control over where these particles end up. We just measure them, right? It's not a cause. It's not an intervention. We don't choose where the particle ends up. And so this story, it's really hard to argue that even with action extremization, that there's anything retrocausal. The field story is a little murkier, actually, especially if you allow for these space-like boundaries of your region, because out here is you, right? You might be outside a region. And what can you do I'm sorry, it's time-like. I said space-like. These are time-like. These are the space-like. If you're out here on this time-like boundary, what could you do? Well, let's put a conductor. Let's put a mirror. Let's put some boundary constraint that actually fixes the field parameters, or some of the field parameters, next to my boundary constraint. That actually, if you then extremize that, actually has an impact of the whole solution. And so it's not at all obvious that the field action story is not retrocausal. In fact, I think there's a very good case to say that just ordinary action extremization on fields, if you allow for these time-like boundaries, actually is a retrocausal story. But I will leave that there. You guys can quiz me about that later. Okay, so let's get into action principles in quantum theory. We have the original Wilson-Sommerfeld, or Sommerfeld-Wilson. Sometimes it's called Bohr-Sommerfeld, but Bohr really just quantized the angular momentum of these orbits. And it was these guys who said, okay, no, let's generalize this, and instead just quantize the action. They didn't really quantize the action, though. If you look very, very carefully at the old quantum theory, it's the action plus this additional term that they said had to be a multiple of 8. And so right away, you're kind of throwing out the invariance, right? In fact, and one evidence of that is it only works for closed particle orbits in phase space. And so if you boost reference frames, a closed particle orbit is no longer a closed particle orbit, and so it doesn't work anymore. So right away, they're sort of picking out this certain special frames, and it didn't seem to work for non-closed particle orbits. But I will make the point that the old quantum theory assumed classical motion. It assumed that these orbits were following some classical dynamics. In other words, this is a 3D action function that is being quantized. And so what this is proof of principle that even after you have done action extremization on the 4D bulk, what you're left over with, this what I call the 3D action functional that just takes boundaries as an input, you can further restrict that and get really interesting results, right? You get a lot closer to quantum phenomena than you were before you put this action constraint. So proof of principle, there's more restrictions that can be imposed. How am I doing on time here?
11:23.
Okay. Okay, so this is going to take a little while, depending on how in depth I want to go into it. But this is now the next bit of the story where Schrodinger comes in and says, okay, I need a wave equation for a particle. How do I do that? So where he starts in his first couple of papers, before the action kind of disappears, see where it disappears, is first of all, he is assuming classical motion. He's assuming the action has already been extremized. Okay, let's back up. Not Schrodinger. Let's start with Hamilton-Jacobi. What is the Hamilton-Jacobi action? Let's assume that we have extremized the action, or the action, and we're left with classical particle dynamics. Those classical particle dynamics are what I've been calling a 3D action functional, in that you put in the boundary coordinates on the surface that you're interested in. Those are the inputs to the action. And those boundary coordinates live in 3 dimensions, not 4. And then you solve for the actual whole space-time region. So let's just do the single particle case. You can see what's going on here. Here's the equation. We should put the picture up here too. Here's the picture. So the picture is easier, right? The picture is I'm going to impose a boundary condition at time t0, the coordinate q0, and I'm going to impose the boundary condition the time tf and the coordinate qm. So these are the inputs to my action function. Those are the boundaries. And then what do? Then I assume that the particle q of t is all the times in between here takes the action extremized path. I'm assuming the action has already been extremized. And so then I solve for this path from this initial coordinate to the final coordinate. And now I get this whole path. Then I take the whole path, put it in, solve the Lagrangian at every time step, and integrate this whole trajectory, integrate the Lagrangian over this whole trajectory, and out comes the scalar. That scalar is the action, right? The action given these in. It's a complicated story, right? We got to think it through. You put the boundaries in, you assume action extremization, you solve for the whole trajectory, you integrate over the whole trajectory, and this total integral, the whole trajectory contributes to S. This is crucial. This is a crucial point. It's not showing up at the end, it's showing up all the way between the beginning and the end. Everybody with me? Because now come the sketchy maneuvers. Okay, that you can do mathematically, you can set it up. But now, how do you interpret this? The typical thing you do now is you fix the initial boundary and you just say, that's it, you can't touch it. But don't touch the final boundary. The final boundary should be totally free. All possible TFs and all possible QFs. And you can do that. You can do it mathematically. What happens is that by fixing the initial boundary, suddenly the action now only becomes a function of that final boundary, right? When is the final boundary and where is the final boundary? And that is the Hamilton-Jacobi action, right? That's what it is. I mean, and it obeys all these nice equations, such as this one that looks shockingly similar to the Schrodinger equation, as we'll see why in a sec, is that there's all classical physics, right? There's all classical physics. But what you've done is you fix the past and you just let the future run free. Now, superficially, you look at the form of this, You say, oh, it's a field. You see why Schrodinger loved this, right? He had a particle and he wanted a field. What does the Hamilton-Jacobi action do? It starts with the particle and you end up with a function of space and time, just like the electric field, right? This is like the electric field is a function of space and time. This S is a function of space and time. It solves differential equations just like the electric field. Wait a second. Is that really what's going on here? Let's think about what happens when you vary the final boundary. So here's the initial picture, right? You have some final boundary QF, some final boundary TF. You solve, you integrate, you get S. What if I tweak T and TF and QF? I change the final time and I change the final position. You go through the same procedure I described in gory detail, right? Where you extremize the action between these 2 points. And what do you notice is that almost always you don't get the same early time behavior that you did over here, right? You get a totally different classical trajectory because you have a different endpoint. And then you integrate over this entire new path to get this new action. Okay, now this does not look like the electric field. This, yes, formally, mathematically, you look at this thing as how it's a field, it's function of space and time. But you look at how you're actually calculating it, and it is nothingness. Because the different endpoints that you're tweaking, the different T's, the different Q's, correspond to entirely different histories, all the way back to your initial value, because you didn't fix the initial velocity, right? So this is the Hamilton-Jacobi action. So mathematically, this is all true. Let's start to interpret. And that's where Schrodinger comes in and buries the action deep into the memory hole of 100 years ago, because this is what he does. In fact, Hamilton-Jacobi people often do this too. Let's just totally ignore the fact that this integral over space and time isn't actually a field located at that final point in space and time. So let's pretend that the whole action is living there at that point, and not where you actually calculated it. And then you make it irreversible choice that the action is only meaningful modulo h bar. So in other words, S of h and S of h bar and S of 2h bar are thought to be not different actions, but be identical. And when you do that, you can define a new function, the wave function, that looks like this. But this is an uninvertible process. You could never get back to S just looking at psi, right? The moment you say S modulo h bar like this, or it's a cyclic parameter, you've kind of forced us into a particular direction that you can't get back from. The other thing that happens here is by going to psi, you just obliterate, and then never mentioning S again, you obliterate all memory. Time t. But that's not what S was, right? S was this integral all the way from T naught to TF, and you change T and you change the whole path. And yet you just hide all that, and you just, oh, this is a field. It's just like the electric field. Right? Okay, so here are some of my rants about all the people that view this psi ontically, that say it's really there, it's really a time t. But this is what Schrodinger does to motivate Schrodinger equation. In fact, I've used this in an intro class, just starting with not like e to the I s over h bar, but just starting with putting an s of like px minus et, and say, let's assume this has got to be a solution of the Schrodinger equation, a field equation. What would that wave equation look like? And you argue your way to the Schrodinger equation. And that's kind of what Schrodinger did. Oh, by the way, Schrodinger did not put the I in at this stage. He left this constant k that he identified with h bar without the I, and he got the I in through sneaky means later. He never really liked the I. He didn't formally put the I in the paper, but it showed up essentially where I have it. And of course, you guys recognize this, right? Exponential e to the I s over h bar. Oh, well, the other things that have vanished, by the way, are covariance, localization, as we discover, and the space-time. As soon as you go to 2 parts, is gone as well. So by burying the action, you've lost all the nice features of the action. But we have, this is the point I was about to make, the e to the is or h bar, that's the seeds of the path integral that basically Feynman and Dirac rediscovers that this is the property that we need to Schrodinger's equation is not the Hamilton-Jacobi equation, right? But it's motivated by the Hamilton-Jacobi equation. And so by this definition, and so this is exactly the factor that Feynman and Dirac found so useful in generalizing this to quantum field for that exact reason. Okay, again, we'll zoom out, take a step back, and even though we've lost every good feature of the action, we've lost the covariance, we've lost the non-locality or the local aspect of the Lagrangian density. What is the success? It still works, seemingly. It's practically successful. The Schrodinger equation, if you add the Born rule, Schrodinger equation on its own is terribly unsuccessful. But if you add the Born rule, the Schrodinger equation and the Born rule is practically very successful. So what does that mean? Does that mean anything about action constraints? What are the implications of action constraints for quantum foundations? And I'll point out that however convoluted this logic I just ran through is, essentially, by putting the Born rule and the Schrodinger equation together, it's still essentially a convoluted constraint on the original action, right? Because that's what motivated it. And so you can kind of unpack it. You can't really unpack it because of this non-invertible step, but there is some kind of constraint on the action. And it works. It says that there are universes that quantum mechanics says a probability of 0. They can't happen. It says there are other universes that are more probable than these universes. And that's also success, right? It turns out some things are more probable than others. And so if you zoom way out, this also is evidence that constraining the Hamilton-Jacobi action in this case gives you a universe closer to our own than you would have thought if you hadn't constrained it. In the end, the predictions of it do respect Lorentz covariance, curiously, but it's not at all obvious why, because they calculate it many different ways in different reference frames. And so the question then is, maybe there's a better way to do it. If you're really just going to constrain the action, why go through this convoluted process? Why not just constrain the action or some 3D version of the action? Maybe not the Hamilton-Jacobi action, maybe some other function of the boundaries that would do the same job. So there's my my motivation for some research I hope to be coming out later this year. And what I'm not talking about the path integral, by the way. The path integral, I'll talk a little bit about later, but kind of restores space-time. But if you notice what the path integral does, is just back to integrating over all possible trajectories. So it's not really a 3D action like the Hamilton-Jacobi action that Feynman's using. He's integrating over all possible paths, crazy intermediate paths. So he's now back to putting in the bulk. And then what do you do? Which bulk you put in? You just sum over them all. And that's really hard to interpret, as we'll see. So there are some really nice things about the path integral, but some things that are maybe arguably a step backward as far as like, why not just start with a 3D functional rather than allow everything to happen in the middle. Okay, so that's the first half of the talk. I threw a lot of stuff out there. Next up is entanglement. So maybe I should pause here and see if I have offended anyone too deeply or any clarifying questions before we get to doing all this for entanglement.
Okay, questions?
Yeah, maybe I am thinking it too mathematically, but when we're talking about action not being a field of space-time, I couldn't really understand the reasoning, because to me it seemed like if you're fixing the initial point, you basically are fixing the A's at all space-time points, right?
So this picture is what I'm talking about.
Yeah.
Okay. So yeah. So both of them are the same initial Q naught.
Yeah.
Both of them are the same initial T naught. Okay. Now what's being varied? What's being varied here final coordinate and the final time, okay?
Yeah.
But it's not the only thing that's varying. If you look at this, there's, when you vary that final point, you vary the whole history.
It's true.
So yeah, you can say, well, let's just take this entire action and condense it on this final point and say, oh, it doesn't live here, it lives here. You could do that, but I think you're kind of ignoring how you calculate it in the first place. You- I'm not offering an alternative yet, but I'm just saying that's a little sketchy. It's a sketchy maneuver to take this whole time integral and assign it to this one point in space and time. That's why I call it sketchy. If somebody on the in the Zoom world has a question, put in the chat. Can't turn on their mic. So.
I don't see any questions in the chat.
Okay.
But can you say a little more about Born rule? I don't see why you put it in. This sounds foreign.
Okay, so where does the Born rule come in? I didn't really talk about the Born rule. I just mentioned that if you don't put in the Born rule, the predictions of the Schrodinger equation alone are wrong. In your many worlds, maybe as you are, maybe you'll say, no, they're right. You just ignore the Born rule. But when I'm talking about a prediction, I'm talking about an outcome of an experiment I can see. So if I'm wrong about that and the other Kens are seeing other outcomes, then maybe we don't need the Born rule. But as far as the experiment to show the entanglement experiment, and I want to explain that outcome, I can't explain it with the Schrodinger equation alone. I've got to collapse it, I've got to put the probability rule on it. And so I need the Born rule. If there's lots of Levs and lots of Kens in a higher dimensional space, maybe they don't need a Born rule. But I'm only me, so I'm gonna analyze the experiments I can see. I do understand where you're coming from.
Now, even in many words, I have to explain the Born rule. I see it in laboratory. So
Right,
right. I don't think there is a difference, but I still don't understand how it's come out. Because
Maybe the best place to answer that is in my entanglement experiment. I'll mention what happens if you don't have the Born rule, what it would predict, and then we'll see where if you just look at one experiment, one outcome, or one set of probabilities, why the Born rule is so important.
Okay, please proceed.
Okay, so that brings us to entanglement. So this is a whole nother motivation for looking at the action. Our big manifesto with Nathan Argaman that was published in Rev Mod Phys in the beginning of the pandemic basically is saying that one of the best ways to think about Bell inequalities and entanglement is, especially if you want a what we call locally mediated account, where there's something happening in between along the places there should be something in between, but not between space-like distances. If you want an account like that, one of the best hopes is one of these all-at-once accounts that looks at the whole space-time block all at once and solves these entanglement experiments like V's rather than like two magically communicating measurements. And of course, the action does that, right? The action is solving a big space-time block all at once. And so we argue in there that it's one motivation for looking at the action. So let's zoom in now to a particular experiment you can do in the laboratory, pretty cheaply now these days. And pretty much if you buy a little set to do entanglement experiments at a university, you're doing something with parametric downconversion. So let me quickly remind you what's going on. You take a laser, you shoot it into a nonlinear crystal. Some of the energy from that laser is dumped into two modes through this three-way mixing process. And there's a K matching and frequency matching, but the end result is that one of two things seems to happen. Either you get mode A's, where you get a horizontal polarized photon over here and a vertically polarized photon over here, or you get mode B's, where you get a vertical one on the same physical space-time path, but with a different polarization, and a horizontal one over here. Later in time, conventional quantum mechanics says this state is entangled, it's non-local, it can't be described as what's happening on the left and what's happening on the right. It can only, according to standard quantum mechanics, be described with this entangled state that looks something like this. Where here A is actually a probability, B is a probability, and so that's why we need square root of A and square root of B here on our thing, so that when we do use the Wharton rule later, we get out the right probabilities of this outcome and this outcome. If that's what you measure. If you just measure H and V, it's easy. It collapses into this state or this state. The interesting thing is what happens if I measure in some other basis. To take a photon and measure at another basis, you just need a polarizing beam splitter pretty much. You set it to some angle, and that angle, really just according to the rules of classical optics, takes these modes and shuffles them so that you get one mode you're measuring on this detector and an orthogonal mode you measure on this detector. And of course, you can do the same thing over here, and you get Bell inequality violations. Now, I'm going to pick one set of numbers here and do a deep dive into that set of numbers. I'm going to pick, and there's a reason I picked these particular numbers. So first of all, I picked a ratio where 36% of the time you generate HV, and 64% of the time you generate VH. And I picked those numbers so that when you take the square roots, the quantum state, according to conventional quantum mechanics, is a nice 3/5, 4/5. So we don't have all sorts of scary square roots floating. Okay, so that's the preparation. What measurement do I want to do? Over here, I want to put this, turn this to a 50-50 polarizing beam splitter for both H and V. So you end up with this plus mode here and this minus mode here that basically measures the relative phase between the H and the V. So that's easily done. Slightly different measurement over here. I'm going to do a 64-36 beam splitter, and that can give you this X up here, or this, and this Y over here. You can do this in the laboratory, and what you see all, there are four possible joint outcomes, right? You measure something on the left and something on the right. But one of those four outcomes is probability 0. So in the lab, you see that you never get a plus outcome at the same time you get a Y outcome over here. All of the other three, you can get plus X, you can get minus X, you can get minus Y, you just can never get plus Y. So I'm going to go through three different accounts of why this might be a 0 probability. First, let's start with the standard quantum account. Standard quantum account says, well, I got to change bases. I'm not measuring in the HV basis. So you look at the inner products with V and plus and V and X, and you do a bunch of math, and you convert this state into this state. And because I picked a 64-36 beam splitter, and because this is 36-64, there's this cancellation, and one of these four terms cancels. So if you notice there's only 3 terms here. You could get a plus Y term, but that's probability 0. Okay, so that's in this basis. That's the original state. So what does quantum mechanics say? Quantum mechanics says, if I first measure photon 1, I could get plus or minus. If I get plus, what's going to happen? I'm going to collapse it to this state, plus X. And of course, you can never get Y on the other side because I've collapsed it here. But if you measure photon 2 first, then you see I can measure X or Y. If I measure X, it collapses to these 2 states, and you can get either outcome on the other side. If I measure Y, it collapses to this 3rd state, and you can only get minus on the other side. So the story of what is happening in between one measurement and the other is different depending on which measurement happens first. But you get the same results. You get the same probabilities, but the story is horribly non-covariant, right? If in one reference frame you get one account, another reference frame you get another account. But they both have a perfectly good account, whichever frame you pick, as to why you never see plus 1. So there's the conventional account. You guys have seen things like this before. Okay, what about the path integral? So let's look at the path integral account. The path integral account says that no, there's no such thing really as entangled state. You just consider all possible histories and you assign each history an amplitude and you sum those amplitudes, a complex amplitude, complex negative number, and you sum those numbers and square the sum. That's the sum over paths or path and over path. If you want to see a nice generalization of this, we have a new paper in Foundations of Physics showing how you can do this with any two-photon entangled state and any basis, and the path integral gives you the right result. Let's see what the path integral does. Here, so so the path integral says one thing has to happen here. Either it's HV or VH. Let's say it's VH. 64% of the time, it's VH. Now, we have to incorporate that probability with some sort of base amplitude of this happening in the first place and use the square root of 0.64, as it turns out, which is 4/5. So we need this base amplitude. And then we say, oh, well, let's look at the paths of the particles getting to, oh, I didn't write plus and y, but getting to this detector up here and this detector here. So here are the paths that the particles take in one history of the path integral. But notice this is a vertically polarized photon that passes through this 50-50 beam splitter entirely and shows up here. Meanwhile, the horizontally polarized photon just perfectly reflects and shows up here. So that could happen, but there's an amplitude for that to happen. To find the amplitude, you pretty much look at this coordinate here, how much of the V comes through, and you look at this coordinate here, this 3/5, this coefficient here, 3/5, and you say how much of the H comes through, and you multiply those together. Why do you multiply them together? Because it's e to the I s, but action is S1 plus S2, and so if you're adding in the exponent, you multiply the amplitudes of these two different paths. Notice there is no non-local connection here, right? It's just path on the left, path on the right. So this is the total amplitude of the history, of this red history. That's the amplitude. But there's another history. Another thing might happen. What if instead it's H and V? Now it looks the same, these blue lines, but don't let that fool you because this is a horizontally polarized photon. If you had split the horizontal and vertical earlier, which you could do, they would separate. And so they wouldn't look like the same path. Here they happen to look like the same path, but they're not really the same path because so, well, what is the coefficient of H coming through? And what's the coefficient of V coming through? This minus just means it's out of phase relative to the amplitude here. So you get a negative amplitude, and then you just plug everything in, square it, and it's zero. You get zero probability of whole outcome has another amplitude because the base of each other is all I don't know. And you get notice distance between the wings of the experiment. You don't need anything going on in here. You just need this funny trick of summing the amplitudes and the histories. And you can do this for every entanglement. There's another paper coming out with showing how this works for entanglement swapping and showing how it works for the triangle network. And we got all sorts of fun consequences. What does it mean? Okay, well, the good news is there's no non-local connection needed between the wings of the experiment. But is this a classical account? Well, no, for a number of reasons. Blue light. One reason is, what does it even mean to add the amplitudes of two totally different? I was telling you the story that there was one black universe, and now we have these two universes. One where it's one for another. This weird calculation, and somehow they cancel each other out. So if you're a many worlds person, this might might guide you down into all these worlds being real. But there are other non-classical things happening here. If you actually set a horizontally polarized photon up here, it would never go straight. This is a 50-50 polarizing beam splitter. It will send 50% of that photon that way. There's nothing you can do about it. There is nothing at all classical about treating the photon like a particle, because classically that doesn't happen. Classically, they split at the polarizing beam splitter. Same thing here. You would never get a vertically or a horizontally polarized photon bending perfectly and hitting this detector. So that's non-classical. Even the preparation is non-classical, because classically, as we're about to see, you get a mix of these outcomes. If you actually set this up, classically, you get both of these happening. You don't just get one or the other. So there's a bunch of non-classical stories here, and I'm going to now argue that they all somehow cancel out, and there is a classical account of this very experiment. And this is this new paper Emily and I have submitted to Physical Review A. I don't know if it will make it, probably a long shot there, but we think it's a fairly straightforward and fun result. So here is the new result, classical account of why this has zero probability. And when I say classical, I mean classical E&M. I mean everything is obeying Maxwell's equations. Anything that doesn't obey Maxwell's equations isn't allowed to happen. I've got to get this process going. This two-way. The first thing is classical interactions in a type 2 semiconductor. And turns out that classically, I just cut and pasted this from the paper, but there's no amplification at all if you don't put any seeds in here. If you don't have any input electromagnetic wave coming in, you classically can get zero amplification. You've got to have at least some energy in at least some of these modes coming in here to seed this three-way mixing process. Otherwise, classically, you get no amplification at all. Classically, you get these equations and the limit that the pump laser is very strong. Notice here I call A1F, and here I call A1I. This is the same mode, but this is the input mode is I, the final mode is F, and it mixes the two modes together. It's three-way mixing. So A2 comes in, A1 comes in, they mix together, and classically this is the gain equation for three-way mixing. You can invert this. It's essentially time symmetric. You're not dumping energy into the parametric, into the crystal. It's just a transitory state of the crystal. You can see that by running it the other way. You can lose energy in this process too. You can have the energy go the other way, depending on the phases. So that's the classical preparation. What's the classical measurement? Well, let's see. Here is my state. Now, this is just going to be done with classical optics, right? You put in the right beam splitter, and it mixes the horizontally and vertically. I left the quantum notation here. It doesn't have to be quantum, right? This is just a mix of a horizontal and a vertical polarized mode. So I want to know why I can't measure a photon here and here at the same time. Well, let's see why. First thing I want to do is
just to clarify, you used the word photon, but I thought we were talking about classical E&M.
Okay, right. So what do I mean by a classical photon? So I mean 1 h bar omega's worth of energy is detected at this detector here of classical E&M field energy. Why can't I detect that here classically? So when I say a classical analog of a photon is a certain amount of electromagnetic energy in the EM field.
I guess, but just to be clear, but in a continuous wave, electromagnetic wave,
yeah,
you'd expect a constant rate of intensity of your radiation coming, right?
Think of a laser spectrum, right? It's not really constant. It could be constant, but it doesn't have to be constant. You could have a pulse. You could have a laser pulse, right?
You could have a pulse. That's true. Yeah.
Okay. Just anything classical is okay. So classical laser pulse.
Okay. Continue.
Okay. Classical laser pulse. Okay. So suppose I measure this energy here. The laws of classical E&M are time symmetric. I can run this backward and say, what does that imply about what is down here. And what it implies is if this is the mode that comes through the beam splitter, the only classical account of this is if down here, this horizontal mode and the vertical mode have the same amplitude in the same phase. If they do have the same amplitude in the same phase, then all that energy, oh, what does that mean? It means they're diagonally polarized, right? You got a horizontal and vertically polarized mode, it's diagonally polarized, which is exactly the angle that this beam splitter is set at, and so it all comes through. So if you get an outcome here, it implies something about these two modes, classical. Same thing over here. If I get this outcome over here, it now implies something about these two modes. It implies that there's this particular angle of polarization at this time. Could be, why not? Why not? Well, let's see. Can that happen? So then you say, well, what sort of, let's go back further. So what's happening here, right? Now, remember I said that there's a 36-64 probability ratio for the HV mode versus the VH mode. We have to encode that somehow classically. But we can do that because there's some gain parameter that each of these pairs of modes have. And all we have to do is set the gain parameters equal to this 3-to-4 ratio. And presto, it now is more likely, or you put more energy, I should say, more energy goes into these 3-4 modes than goes into the 1-2 modes, and it comes in with exactly the right classical ratio of energy if you put these in. Okay, so now you take all these restrictions, you plug them back in those equations I just showed you, and you calculate the relationship between the total input intensity, the square of these 4 modes, that's IN, and you look at how they're related to all these output modes. And look, A1 squared, A2 squared, A3 squared, A4 squared, that's the final output intensity. Now you may be worried here, wait, cosh, hyperbolic cosine, that's always at least 1. Same thing here, this cosh is always at least 1. So that means actually, if you ignore this last term, the I in is actually bigger than I out. You've lost energy in this process, and that can't happen, right? The whole idea was you're putting energy from the pump into these modes. But this last term can normally save you. This last term can normally make it where, yes, there is energy going from the pump to, but you put in all the numbers and this cancellation happens just because of the exact numbers, the fact that this is a 0.6 to 0.8 ratio, and the fact that this is 64 to 36 ratio. You put it all in, and the epsilon term you expect to balance out the to make us positive goes to 0, exactly. The only surviving term here is an epsilon cube term. And so in the limit, you get small signal gain, and it turns out in the big signal gain limit, you can never get gain into this precise mode. If I just tweak this angle slightly, 65-35 or 63-37, you can make, then they don't balance, and then you can actually have gain. But at this exact setting, there is no way to get gain from a pump laser into 2 classical modes that match this detection. And so the surprising result is that you can get these 0 probability joint outcomes from classical EM. You don't need path integral, you don't need quantum mechanics. All you need to do is think about this entirely classically from classical field account and say, oh, it can't happen without somehow the gain going in the wrong direction, dumping from the mystery seeds to the pump. Now, you might say, wait, where do these mystery seeds come from? Well, remember how I mentioned the old school uncertainty principle? The old school uncertainty principle applied to classical E&M fields says you can't actually know there's no field here. We call it the 0-point field in quantum mechanics, but you can't actually know there is no field coming in there. And so since you can't absolutely know that for sure because of the uncertainty principle, there could be a field. But it doesn't matter whether it is or not, because the whole point here is that there is no possible input field, no conceivable set of these 4 input fields that will both give you gain and show up where these 2 photons show. Nothing non-local, nothing multiple worlds. This is a single world story of why this can't happen. I did it. I made it to the end. We still have time to talk. here are my thoughts. A lot of this is sort of a setup talk for other stuff. But one thing I will stress is that all of these no-go theorems, that you can't do things like this with classical hidden variables, assume that you have this Hamiltonian story or this Newtonian story where the hidden variables are causing the next thing and causing the next thing. You're solving the universe like a computer. If you have these all-in-one action constraints, and there's some effective retrocausation where the choices of your settings of your future beam splitters are somehow constraining what's allowed to happen in the past and some hidden level. I'm not talking about backward signaling here. I'm talking about effective retrocausation. All the no-go theorems fall apart, and that's, you can read the gory details in the RevMod Phys paper with Nathan. But given that, there is no technical barrier to making an action story of all this work. If we are going to make an action story of all this work, and this thing I showed you is just one tiny piece, why is it zero probability? It's not the whole story. But we can be creative with the action. Why do we have to always constrain the coordinates and never the derivatives to get Euler-Lagrange equations? There are, in fact, and you can find a paper of mine in the archive showing one way to do this, other constraints on the action that will also give you Euler-Lagrange equations that are more choice friendly. You can choose at this boundary or that boundary. Why only look at Hamilton-Jacobi 3D actions? Once you extremize the action, why always fix the past and vary the future coordinate? Once you start having derivatives in there, or action angle variables, or other cool ways to write the action, there are other 3D action functionals we should play around with. Once we have those different functionals, let's try other constraints. We don't have to always go to the Wilson-Sommerfeld constraint that doesn't really generalize. There have to be other ways to put H bars on the action than have been tried so far. And once you do that, maybe there's a different probability rule other than summing over all these histories. Maybe there's a one world all at once probability rule other than Feynman's rule. And I actually have answers to all these questions and ideas for all of these, but that's what I said about setting this up for future results. So the future results I think you will see this year are the one with Emily Adlam I've already mentioned, that you can do this to get all zero joint probability cases for all two photon states. The next one is going to be the photoelectric effect as an action constraint, which I'm very excited about. Seems very, very different topic, but it's coming out nicely. And something I discovered last summer that I'm still trying to extract properly is that in the classical field actions of these very experiments, these classical field experiments I just showed you, for the non-zero probability outcomes, the right probabilities are hiding there in the math in the classical field action. And if we find out the right rule to suck out those probabilities, I think we'll have it. I think we'll have the one world account of entanglement, quantum theory. We'll have it all. So I don't have it to show you yet. I'm not even sure what it is yet, but that's the plan. So stay tuned.
Okay, let's all thank Ken for this nice talk. All right, so for people on the Zoom, if you'd like to ask a question, you can raise your hand. So I think Lev Weidman has his hand raised. So why don't we start with Lev?
Can you come back to the previous slide? You're kind of
yeah, my classical story here.
Yeah,
and Emily,
yeah.
Oh, hi, Emily.
So I just want to be sure I understand what you want, what you claim.
Okay.
There is some preparation procedure. You put some pulses in with all these amplitudes and whatever.
The only thing you put in is a num. Everything else is just background seeds. Yeah.
What?
The only thing you put in here is the pump laser beam. You put that in. This other stuff here is just there. It's just background seeds.
Whatever, you do something there. Then
Okay.
there is this device which you have, which can be long distance.
Yes.
And And then you say that you somehow classically can tell me about correlation.
Yes.
So I'm in a space. We are very far on the left and right laboratory are very far, and then and you say that you look on these things which are supposed to be dark, and you say there is some classical thing. Usually, classical it's some field. So field is either there or not there. So if instead of h plus v on the left, it's h minus v, then it's there.
Then it shows up here.
Plus v, it's not there. So but after this pulse, there is some classical things in h minus on the right where you say it's dark or not, because how you get correlation, I still don't understand. If there is a classical field, I still don't. But you say that every time when you prepare it, there are something different. Sometimes you send, so on every run, you will say you will have h plus v on the left and h minus and h plus v on the right, because h minus v cannot be, or maybe not. And on some other cases, you will have some other things. So you do your preparation, and every time there will be different preparation. You're saying there is some randomness in preparation. This is what your idea? Well, what do you want to say?
Okay, first of all, I will zoom out and say, I'm saying that these two things can never happen together, even though they're very far apart. But there are plenty of classical analogs of that. If I deal playing cards out and mail them across the country, two people are never going to open from the same deck. People are never going to look at the same card arrive in their mailbox, right? So there are plenty of classical anti-correlations. It's not hard to come up with a classical hidden variable account of two things that can never happen together. And that's all we're getting here, is that these two things can never happen together. Okay. So that does not.
What happened if there is a field? You make your preparation, whatever, and if there is a field on in the detector of h minus v, or there is no field, what will happen? Just you send it. Don't measure anything. You say it's classical. If it's classical, as I understand, either there is a field or there is no field. So there is a field or there is no field.
Okay, the way this proof works is you assume there's zero field on this detector, on the dark detector, and you assume there's zero field on this dark detector. And then you say, well, what possibly might have made that happen? And what possible input seeds might have made that happen? And there are no input seeds that can make that happen if there's gain in the parametric down conversion. So the story is that you assume this is dark and this is dark, and then you say, well, how could that have happened? And you go back, and there's no way it could happen. There's just no classical account of it. And so you say, well, it can't happen. It's zero probability. But
just to be sure, if I understand you correctly, you say every time you go to laboratory and make this pulse, you really prepare something different because there are some hidden variables. This is what you want to say?
Yes, there is some randomness here, but again, we're not explaining the other three outcomes. We don't yet have an account, a good account, for the other three outcomes that have non-zero probability. So we're not talking about the cases that can happen. We're talking about this one thing that can't happen, and we're trying to explain it classically. That's the idea. Now you're right. That once you move to things that can happen, it's going to be harder. But at least this works. That what can't happen matches classically in quantum mechanics.
So you explain what's not happening, but you do not explain the whole statistics of what's supposed to happen.
Correct.
Okay.
Correct. Yes. Not yet. Wait for it.
Okay. So we have another question from Kai Wagel. He asks, is there an explicit unspecified dependence between the future measurement settings and the seed field?
In this exact case, that's a great question. Oh, you want to expand on that?
No, I don't. It wasn't even a question. It was just, I was sort of trying to solidify what you had said. This was as I understood it, and Emily seems to have confirmed what I was saying.
Oh, I see.
kind of-
Yes, you answered your question. So whether or not, I mean, in the future thing that what Lev pointed out we haven't done yet, if we do that future thing, it will absolutely be the case where the future settings will somehow constrain what these past seeds are allowed to be. Yes, but in this paper, we didn't need to do that because we just got to look at all possible input seeds and say there are no possible input seeds that will make this happen. So we say, therefore, it can't happen. We don't even have to address the fact whether these seeds are real. We just say, even if they are real, it's still can't. So if we don't have to for all the non-zero cases, we absolutely will have to be retrocausal.
Can I have a question about this same setup? So it seems to me that if I had a classical description of what would happen if I put a classical pulse of light into this this parametric diamond conversion, what I would find is if I put in some energy E into my initial pulse, I would see the initial energy divided by the multiple vector according to actually force reduced by the relative. That's right. That's correct. Yeah. And so whereas it seems like a quantum description would be that not all four detectors click, only one of them clicks with the same energy that I input, right? And so how does that observation enter into?
This has no account of that. Classically, if you put most beams onto this beam splitter, both of these detectors will fire classically.
Yeah, all four.
It's almost as if we need some sort of new constraint to keep that from happening. Maybe on the action. But we need something else to solve that problem. Absolutely. But here we work backwards. Here we said, suppose this is fully dark.
Yeah.
Then what does that imply?
I see.
Right.
I see. So if you only want one detector to fire, what has to conspire to make that happen?
Right. That's the question.
Right.
What action is there an action constraint that would only allow one detector to fire? And that story we actually pretty much have. So that will be coming out later this year.
Okay. Other comments or questions in the room? No? Anything else from the chat or in the Zoom? Okay, if not, why don't we thank Ken again for this nice talk. And if anyone wants to join us for lunch in the faculty club, if you're here, you're welcome to do that.
Thanks for joining me virtually, everyone. And shoot me an email. Also, we have a paper is actually done and submitted, so I can send it to you if you're interested.